Hello, everyone. I am Xuan Gong from University at Buffalo. I will introduce our work Uncertainty Learning towards Unsupervised Deformable Medical Image Registration. Uncertainty estimation in medical image registration enables surgeons to evaluate the operative risk based on the trustworthiness of the registered image data. It is very important for practical clinical applications. Despite the recent progress in deep unsupervised learning-based registration methods, uncertainty estimation of unsupervised registration models remains underexplored. We propose a novel framework which combines empirical randomness and registration error for uncertainty prediction. We propose a predictive module to learn the registration and uncertainty in correspondence. We systematically evaluate different combinations of empirical uncertainty and predictive uncertainty. The registration network is to learn a registration flow from moving image I to fixed image I. Then the registration flow is used to warp the image I to align with the fixed image I, so that the two images can be registered in the absence of ground truth. We use normalized local cross-correlation as loss function to evaluate the similarity between the warped image and fixed image. We used Tversky loss for the segmentation reconstructed loss. Furthermore, we penalize the local spatial variations in the registration flow to constrain it to be smooth. We model the distribution of the registration flow as Laplacian distribution, and learn the model through log likelihood maximization in the case of one Lyra loss on the registration flow. This can be also written as negative log likelihood minimization. With the absence of ground truth of registration flow, we learn to encode the reconstruction error in terms of segmentation labels. We use this to represent the uncertainty or ambiguities of the registration flow. For empirical uncertainty, one intuitive way is bootstrapping. By randomly sampling a subset of training data, we can train n-independent models. By enabling dropout during inference, we can get n different inferences on one trained model. A third way to get empirical uncertainties is through n snapshots of a single training instance with cyclic training. We can get multiple predictive model with the aforementioned empirical methods: bootstrapping, dropout, snapshot. We get the empirical ensembles of the individual flow and uncertainty prediction. We experiment on hippocampus dataset and prostate MRI datasets. For registration metrics, we use mean square error, mutual information, normalized local cross-correlation between images, and dice coefficient between labels. For uncertainty metrics, we use the area under the sparsification error curve. In terms of the average voxel-wise error, miss rate and false discover rate. Sparsification plots are used here to represent how much the estimated uncertainty coincides with the true errors. If the mean error monotonically decreases when the pixels with the highest uncertainty are removed gradually, the estimated uncertainty is a good representation. We represent the true uncertainty with the voxel-wise error between the warp label and target label. This is called oracle sparsification and marked in red the figure. To quantify the sparsification error, difference between the sparsification and its oracle, we use the area under the sparsification error curve, OS, as the metric of the uncertainty estimation. On hippocampus dataset, the figure in the left compares the area under the sparsification error curve, OS, where the sparsification error uses averaged voxel-wise error, AIR. It shows our predictive model significantly improves the uncertainty estimation with smaller OS. The table shows our predictive model significantly improves the performance on 4 registration metrics: MSE, MI, and LCC, DICE. And it achieves the best OS as uncertainty estimation when the predictive models are ensembled via snapshot. We can see from the table that our proposed uncertainty model outperforms voxelmorph on prostate dataset. Our predictive method combined with snapshot empirical achieves the best performance on both segmentation metrics and uncertainty metrics. Thank you for watching. For more details, please look into our paper.